Welcome to the Mathemagic channel. Today we're doing a super cool video to react to Animation v Math. Now for those of you who don't know, this is a very largely viewed video with over 50 million views. It was produced by a guy called Alan Becker. It is absolutely mind-blowing. And so in today's reaction video, I'm going to do my best to explain some of the secret hidden meanings that maybe we don't pick up on at first glance when we look at this video. Anyway, enjoy the video, don't forget to like and subscribe, and let's roll the tape. Here we go, we start with a stick man. It all starts with the number 1 and the equal sign. Fun fact, we use the equal sign because nothing can be more equal than two parallel lines. This is pretty self-explanatory. He discovers addition, repeated addition, adding lots of ones. That's quite time-consuming. Bigger numbers, it's going to help to move faster. Oh, don't be sad. Is he feeling lonely? Discover subtraction. Very cool. And the zero element. And now into negative numbers. Oof! What's this? E to the I pi. So in mathematics, there is such a thing as Euler's identity, and it says that e to the I pi is equal to -1 because it's 180 degrees away from 0. So it's on the negative side of the unit circle. So first cool bit of mathematics here, e to the I pi is -1. Oh, e to the I pi is running away. And what happened here? So he's a real number right now. E to the I pi is still a real number. But if you multiply it by I, you become imaginary. And there's kind of this portal gate here. And it looks like he's just gone into another dimension. Let me know in the comments below if that's what you think happened. I think he's just gone from the real numbers to the imaginary numbers. And now our stick man is back with his real numbers. But he's all alone. What can you do? You can add some negatives. 2 negatives make a positive. Times. It's going to turn that symbol sideways. Yeah, we can multiply. What's going on here? 3 times 1 plus 1 plus 1. Okay. 3 times 4. 4 times 3. Okay, so 4 times 3, 3 times 4, these are the same thing. 2 times 6, 6 times 2. We're highlighting what we call the commutative properties of multiplication. You can do it both ways. 2 times 6 and 6 times 2 is the same thing. So we're looking at number sets and properties of number sets. Division. Whoa. Oh, dividing by 0, we're breaking mathematics here because when you divide by 0, you shoot off to infinity. You can't do that. Don't break math. Brackets, square numbers. 6 plus 2 squared. What's all this? Oh, okay, yeah. I think in this section he's talking about these algebraic identities when you do a plus. And by the way, these are beautiful visual representations, or this is a good visual representation of, you know, adding two sides to a square and multiplying it by itself to make like a like a bigger square like this. So a plus b squared, a minus b squared, and I don't think that this showcases the difference of two squares, but I might be wrong. Yeah, very nice visual representation of that here. So a minus b squared, square number. Oh, to the power 3, so cube. Wait, what is this? 4 to the power 4? I think we're talking about tesseracts now, hypercubes in 4-dimensional space. Now here's a representation of a hypercube in 5-dimensional space with triplets. So I'm not too sure. If you think that this slide is kind of representing hypercubes, then please let me know in the comments below. Okay, this is really exciting, you guys. Wow, I have no idea where we've gone with that. Okay, 4 to the 5 is 1024, pretty cool. Subtracting powers. 4 to the power 0 is 1. Negative power means inverse, which is a fraction. I suppose we're going to see square roots next. 1 over 2. Yeah, so the square root of 4. Fractional powers. Powers is fractions. Roots. Root 2, 1.414. 2, very nice. Square root of 1 is 1. Square root of 1 is 1. This is going to be I back to negative numbers because I squared is negative 1. So the square root of negative 1 is I. Adding complex numbers, multiplying complex numbers, and E is back! E has just appeared out of nowhere. Oh, looks like an angry doggy and they're gonna have a fight. Why is he fighting Isaac? Are they going into another dimension? There was a brief moment where there's an appearance from cosine. Did you see that? Sorry to rewind it twice here, but I'm trying to catch it. Oh, where is it? Let's catch it. Cosine pi plus I sine pi. Oh, very cool. As you can see, we can express e to the I theta as cosine theta plus I sine theta. So this is a kind of representation of that. Oh, so it was the negative version of it. And now he's shooting his negative sign at the stick man. He's gone e to the power 0, full semicircle on him. There's a lot of detail here. So much I feel I'm not catching up on. He's got the multiplication sign, which makes him run faster. He's gone full tribal, you guys. And he's made him negative. Negative against positive, like a cross. Is that +1 and... Wait, it's +1 and -1 fighting and creating zeros. That's very cool. Oh, he's turned it into a 4, so he's more powerful, I guess. And then he's got a 2 times 2 and a 2 times 2. He's shooting 4s at him. Oh, wow. Now, e to the I pi over 4 is a quarter circle of 45 degrees. So he's gone up. I guess he's on the imaginary axis now, while our stickman is still in the real numbers. Oh, so if he multiplies himself by I, he can go into the imaginary numbers too. And I guess he's done just that. He's taken a big leap. This is absolutely incredible, you guys. Oh, so we have the imaginary axis here. So the vertical axis is the imaginary axis. And the real numbers, okay, I guess we need a unit circle, don't we? Yeah, okay, that makes sense. Let's represent all that on a unit circle. So you see 1 radian, 2 radians, 3 radians is almost 180, so actually pi radians is 180. But notice the 344 here, which shows you exactly how to convert 6 radians into degrees. That's pretty cool. I mean, it's just another representation of Euler's identity. This is an arc of 1 radian? Okay, so in math, when you do theta r, you get the arc length. So when you multiply the angle by the radius, you get the length of the arc. An arc is a piece of a circle, you guys. So here we have a circle with radius 5. If we increase the radius, we increase the circle. We can do it both ways. Oh my god, so much to unpack here. round and round on the circle, making it smaller. Oh, have we just discovered pi? Theta divided by r is pi. Very nice. Oh, what is this? So cosine t and sine t. Sine t is a curve and cosine t is a curve. So I guess we're going to see some curves. That is the period of the sine function. Goes in 2 pi radians, and then t on the vertical axis here. And we can combine them. Very nice. If you multiply by I, that's going to go vertical because it's imaginary now. Oh my, there's so much here. This is so creative. And it's actually really good to learn math. Oh, so we use Euler's identity again with the cosine and the I sine to change back to e to the I pi. Whoa, 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 whoa. Okay, so who's this, you guys? This is the sum from 0 to infinity of I pi to the power n over n factorial. Now, it is interesting to note that e to the x does have a Taylor series expansion, which is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on and so forth. So when you have a Taylor series expansion, which is I pi to the power n, if we go back to the one in the video, so notice here that we have I pi to the power n over n factorial. And so if you were to change x from e to the x into I pi, you would have e to the I pi. So this looks like it is the expansion of e to the I pi as Taylor series. Oh, shooting stuff. Shooting I pi squared over 2. He's shooting his terms, you guys. Are these the numerical representations of those terms? Oh, wow. Can you imagine how long this took to actually find the decimal value of whatever term this is? This is when n is equal to 10. So this will be like I pi to the power 10 over 10 factorial, plugging all that in, making it into a beautiful explosion. That is absolutely insane. What a crazy amount of work, you guys. I mean, we have to appreciate the beauty. Whoa, whoa, whoa. So he's got a shield, which is his unit circle. And if you multiply it by 8 pi r squared, you get a cylinder. You get very cool. 3D shapes. E to the I pi is having none of that. He's like, I'm going to make my circle bigger. He's like, okay. He's trapped in the circle. Oh, he reappeared on the other side. He just kind of negated himself. He's being chased by that Taylor series again. Knocking him out with a sine curve. Not happy. Oh, that. Oh, what's this? So you notice we changed cosine plus I sine into e to the I pi plus e to the minus I pi over 2. So in math, you can change sine x into e to the ix minus e to the minus ix over 2i, and you can do the same for cosine. I guess this is what's happening here. Okay, let's see where this is going. Oh, so we can keep changing them back and then expanding them and making them bigger. There's no limit to where you can go, really. You can just keep expanding and making them bigger. I think I missed something here. So he's got 9 times... Oh, sine over cosine. Okay, well, another point here. It just goes to show how much good stuff there is in here, because sine over cosine is tangent, you guys. So you can see we have representations for tangent and cotangent, sec and cosec. And so here we've decided to divide sine by cosine and get the tangent curve. Now, I don't know what we're going to do with it. Sure enough, we change it into the tan function. God, he's shooting tan waves. Can you see that? He's got his tan gun and he's shooting little tan waves. Wow! he's used the 7i to go up because he's going on the vertical axis. So every time he wants to go up, he uses a bunch of imaginary numbers. And he steals the infinity sign. What's he gonna do with it? So these are like infinite tan waves, and as you can see, it looks like he's escaping our world. So there's R1, R2, R3, R4, the real numbers, and then R cubed in 3 dimensions, and R4 maybe including time. And so is he going to exit the 4th dimension? Oh my. So this is like the sum monster with lots of different expressions. Maybe drop in the comments if you can see what the expressions are, and if you know how much they add up to, or how much they come out as, then probably drop that in the comments below. There's a lot of expressions here. There's a big integral symbol, and e to the 3i, and then some integrals which are related to some values here. There's some limits, which might be interesting to look at. Lots of expressions hidden in this image. Maybe have a look at it, see if you can figure anything out. Get back into the real numbers. These multivariable tan waves are too strong. Just way too strong. I think he just increased the radius, and he's just gonna go massive. Trying to escape to another dimension. So these are all the square roots of negative numbers. So I guess he's in the imaginary numbers right now. I think we might have just broken mathematics, you guys. Stickman broke math. Please don't break math, Stickman. We need mathematics. Oh my, this is crazy. Adding real numbers. With multiplication by I, he escapes through the portal. So he wants to go through a doorway. Have you noticed how this spells exit? That's a neat little trick here. Get in there. Oh, the gamma function. So for the super nerds in here, the gamma function is here to express the factorial notation for complex numbers. And I guess we have a representation of it here. Now, what are we going to do with our gamma function? We're putting him in a little... We're increasing the 2n value. 2n goes to infinity. An infinite number of circles around Stickman. He's now in a sphere of light. He's like, bye, and then we multiply by I and something's happening. Oh, because we multiply by I, he sends him in the other dimension. He sends him back into the reals. Hang on a second. He was in the imaginary numbers. He wanted to go back to the real numbers. And then we had the gamma function and we multiplied it by I which was a factorial representation in the complex numbers. We multiplied that by I and then he goes back to the real numbers. My God. And here we have phi and we have we're going to have phi and delta and the zeta function. I guess they're his friends, right? But he's real right now. He's not imaginary. What's this big shadow at the back? Wait a second. There's a big walking shadow at the back. Do you see that? Okay, I think... Again, you guys can confirm it or not. I think that we're talking about Aleph in the background, and Aleph is there to, the Aleph number is there to denote the cardinality or the size of a well-ordered group. So if you think that that's what it is in the back, then please let me know in the comments. The plus end. Wow, you guys. Absolutely incredible. Okay, so much to unpack. First of all, I hope you enjoy the video. Second of all, if you have anything that you've seen that I missed out, and I imagine that's like 99% of the video, then please put it in the comments. I'd love to hear your opinion. I'd love to hear what we missed out and, you know, try and understand and appreciate this video better. Third of all, the point of the video, what do we think it is? Well, it's kind of humanity, right? Like this human stickman discovers addition, multiplication, subtraction, all the operators, the zero, the negative numbers, commutative rules. He manages to make, you know, like exponents and cubes and hypercubes and things like that. Then he discovers complex numbers and an imaginary world. He transitions. Maybe he grapples with it a little bit. Like, is that a representation of him struggling with complex numbers? Because for centuries, they weren't really accepted. And, you know, people thought that they were a fallacy. So is this like a historical representation of how he felt? Let me know again in the comments if that's what you think happened. Really interesting to see how he transitions from one world to the other. And then how at the end, maybe he's like, get me back to the real numbers, get me back to a world without imaginary numbers. And then how, you know, everything has to do with number groups. When we see Aleph at the end, does it just have to do with homomorphisms and isomorphisms and essentially group theory? So is the most important part of mathematics group theory? Is that the superpower? I don't know if you're a professor at university and that's what you study. Maybe you can chime in here. But it seems like group theory is just so powerful because all these operations that we accept, we only accept them in certain groups. So as long as you're working within the real numbers, you accept a certain type of algebra. And if you work in a different kind of space, then suddenly all the rules change, whether it's like matrix addition and things like that, or whether you're working with complex numbers. I really hope you enjoyed this video. I hope you enjoyed the little points that were pointed out for you or highlighted for you. Please make sure to like and subscribe to the Mathemagic channel, and we shall see you on the next video. Thank you so much. Bye-bye.